Well, good afternoon. Thank you very much indeed for turning up. I'm very much looking forward to this event. If I speak too loudly, bear with me. I had to go for the microphone because my throat is a little dodgy. Now, first thing this morning, I thought I'd have a look around and see how lectures are given, and was duly confused. So please bear with me. I'll do the best I can to share some of the experience that I've had in my career in the markets that in many ways are more demanding because they're quite highly regulated or very constrained in the way they finance things. So I thought this would be a useful topic to talk around and hopefully to build on the previous presentations that have covered some of the other aspects that you're thinking of as budding entrepreneurs. So what am I hoping to achieve today? Innovation is in my lifeblood. I really believe in it. I believe in new products. I believe in new ideas. I believe in taking concepts through to market. It's what I've done throughout my career, and I'd encourage you to consider doing that in your own future careers in a variety of ways. I'd like to consider innovation. I know that it's been discussed in previous talks, and I will have to cover some ground again because it is worth reinforcing those points. But there are some constraints in some of the markets that I will be looking at. In some of these difficult markets, in many ways, it is not easy as a small company or an individual entrepreneur to penetrate them. But there are ways around, and again, we might like to discuss how that could be done. I'll share some personal experiences. I've got a few examples of things that I've developed as part of teams in the past, and I'll try and extract a few lessons on innovation strategy from those. And as I've said several times, I encourage you to be entrepreneurial, to get into the field of developing new products. It's exciting, it's fun. What do I mean by entrepreneurship? Perhaps a little different, and I'd like to broaden it a little bit. To me, there are two key aspects to being an entrepreneur. One of them is innovation, and the second one is a willingness to take risk. And those two put together allow you to take your ideas, your abilities forward, your capabilities forward in different ways. As individuals setting up companies, in small teams as part of an innovative company, but also do remember, large companies may take a lot of stick, but they are innovative. They often have to work within constraints, but there are often reasons for it. Now, I know in the last talk, Josh described the way that he is helping large companies to innovate, and I think that that will continue to happen. But do bear in mind, you don't have to be a one-man band and I'm going to do it or fail. No, there are environments in which you can work, and consider them all before you charge into the difference between an idea and a product. So, we've had earlier talks within the Future World concept, and I just highlight three which caught my eye as I looked through the site and as I reviewed some of the earlier talks. I think Budge was quite right. You don't have a product if you can't sell it. So it's important to understand your route to market, and I think he gave you a very good introduction to that. Chris highlighted the challenges of dealing with big business, and to some extent I'll be building on his thoughts to explain some of the constraints that big companies have in demanding markets. And finally, Josh gave a really inspirational talk in making innovation happen. And I'd like to build on some of those points that he raised and share perhaps a slightly different perspective on the same challenge. So I've shared my objectives with you. I'll go into my personal background, build a little bit on what was said a little earlier on my own starting point, and give you the context for innovation, and then consider the demanding markets. The lessons that I've learned are quite specific, and I won't pretend to answer or even consider many of the issues that you have in taking your ideas forward. Now, you have a tremendous environment within the University of Southampton, both through the research and innovation services, through Future World, and my thanks to you both for giving me the opportunity to share my career with you and some lessons from it. But I certainly can't pretend to answer all the questions. I will look at some examples in these areas because those are the ones I know fairly well. I spent about 8 years in semiconductor R&D instrumentation, 5 or 6 years in medical electronics, and I better stop there or I will convince you I'm a dinosaur. And then I'll just give you a quick summary at the end. I have more years experience perhaps than I care to admit in engineering, industry, and also in the Army Reserves. I find that I get stale if I've been in business or in a particular area for more than 3 to 5 years. I need a new challenge, and I've been fortunate to be able to do that in the past in my career. Really, I'm now very much in the strategy, systems engineering, and merger and acquisitions area in my consultancy, and I'm helping UK companies and international companies in those areas. I held the Chief Technology Officer position in Vickers and in Cobham, very different companies. Vickers was absorbed into Rolls-Royce PLC, and I helped that transition, which was interesting, but I think I won't say too much about that just now. And Cobham is an exciting company in aerospace, defence and communications. Ruben has mentioned general management experience. So when I talk about innovation, I do understand the context. I'm not just a thorough engineer or a deep technical specialist. I have worked in the general management experience. And recently, I've been heavily involved in the design and implementation of the Aerospace Growth Partnership, the Defence Growth Partnership, and I have strong links still into various government departments, EPSRC, and some universities, and I'm delighted and very honoured to have strong links with Southampton. Started consultancy a year and a half ago, currently working at the Aerospace Technology Institute, which is hosted up in Cranfield, but it's the UK's strategic institute working on commercial aerospace. It's a joint venture between UK industry and government, and has a very large budget and is actually doing some very, very good work. I've been working on topics such as the UK strategy for aerospace systems. I've been looking at the all-electric aircraft. I've also been looking at some of the challenges with setting up an aircraft-level simulation environment within which we can test UK-developed systems. And most recently, and now totally out of my depth, I'm looking at some of the challenges in cybersecurity in future aerospace, focusing on the aircraft, the systems on the aircraft. So I don't pretend to understand the broader cybersecurity of, say, an airline, but I'm looking at the aircraft and the challenges there. I've been working with the University of California in Santa Barbara, I'll mention that later on, and a number of large and small companies. Right, so that's given you a why I'm here, and I hope you accept that I hope that I can give you some value and some insight that will help you in your future careers. Innovation. Now, Josh, in his talk, challenged the definition of innovation. That's what Wikipedia says. And it's right, but it's not helpful. So perhaps we can view it as, in this definition, the application of better solutions that meet new requirements, unarticulated needs, or existing market needs. Don't really know what that means, but I think it's a good starting point. So let's think about some of the phrases. Better solutions. And that is, whatever idea you have has got to offer and has got to be better in some ways. It's got to be the better mousetrap. Better is defined in many ways. For example, in aerospace, if we look at better in terms of propulsion systems at the moment, the key drive is lower emissions, more efficiency. So a better gas turbine engine is one that would have those characteristics. So when you have your ideas, just think about what does a better solution mean in your context. New requirements. Are you creating new requirements, or are you fulfilling existing requirements better? It's an important question, because if it's something new, then your challenges in getting your product to market are a little different. Is the market ready for it? Is it an unarticulated need that the customer has always wanted, doesn't realize they want? So the marketing side is important, and that's why Mudge's presentation was so relevant. You have to understand the front end before you take the plunge of developing a product. And the application is the final one. And that's one I will refer back to in this talk as we go on, because the application may have constraints. I mean, if you have a better biro, then all it has to do is be a better biro. However, if you're working in the medical field, then your idea has to not only be safe, but it has to be efficient. It has to add value to your patient, not be a whim that he buys because he likes the color of the biro. So you need to think through the application as you're developing your ideas. New product development is the reason why we do innovation. We're trying to create new products, create new markets, and frankly, at the end of the day, make a profit. So you need to think through the various ideas. Now, most of you will be at these stages, and that's quite right. But you cannot ignore the rest of the new product development process. And I think that is perhaps the one message I'd like to leave you with. It is important to think it all the way through from concept to product. At the front end, yes, fuzzy, flexible, you're not quite sure exactly what it is, you just know you've got an idea. At the far end, it has to be physical, it has to be focused, and it needs to be fixed, or else you'll never make it and make money. So think that through. That has implications. So the first thing that perhaps you're familiar with, but if not, you should be, is the concept of technology readiness level. So when you have an idea, where are you? Is it totally just you understand the basic principles, they're observed and reported? Is the first articulation formulated? Are you getting to the stage where research is proving feasibility, or are we further up the scale? There is a reason for saying this and for sharing this with you. This area here between 5 and 7 is difficult and expensive. I'm afraid that ideas generally are relatively cheap, and you can take them through the first few stages fairly easily. Do not underestimate the cost involved in converting a technology a prototype, a simple concept demonstrator, through to something that is marketable and sellable. And that, unfortunately, is the case in some of the markets that I will be considering. Universities and academia typically work at the low TRL levels, and that is where they should be. You are the generators of ideas. What I'm hoping that you will take from this talk is when you leave here, you will make sure that you think through all the TRL levels through to production and service. It is important to understand the concept. You don't have to have perfect answers, but you need to understand the challenges, and just as importantly, question any assumptions you're making. You cannot assume that there is a manufacturing process for your little gizmo. You need to challenge that and think it through. You cannot assume there is a good route to market for your gizmo. You have to think that through. So please think system. Think the whole process through from concept to product. So we focus on these. You're good at it. You've had earlier talks on them. You've thought through your market. You're thinking through the way that you can develop your product. Be a little careful. A product development process can be complex, and in many ways it has to be if you're going to meet some demanding markets. I don't expect you to read this. The whole point was just the point of the diagram is to make the point that a product development process is required, and it often can be complex for some of the more demanding markets. Even one of these will have lots of subsets, test procedures, proving that what you're making works, proving it can be integrated, and proving that you're generating the reports that may be needed by the regulatory authorities. So as I say, don't get weighed down by a complex process, but be aware that it may be necessary, and you need to factor it into your thinking and your financial planning between concept and product. So some key takeaways from those first bits. As Mudge said, understand the market needs and positioning. That is key. If you don't understand what your product might offer your customer, don't go ahead. Think that through first. What you really want is market pull. Technology push is much harder than market pull. So evaluate many ideas. Question your idea. Can it be done differently? Can it be done better? Has someone done something similar that will compete with you? So evaluate many ideas, think around the subject. Make sure you understand why your product is better than someone else's, because that, again, will give you the differentiators that will allow you to get the investment to take it through to market. Now, my experience is in larger companies, so often it's a case of putting together a business case to sell internally. You have a slightly different challenge if you want to be part of a smaller company, and you may have to interact with venture capitalists. But make sure you understand your differentiators. Question your assumptions. It's obvious, but it isn't. Make sure you understand what it is you are assuming when you're designing your product. You may be assuming a manufacturing process. You may be assuming the availability of a technology. Just question them. Be careful. That is where, when I've worked with companies in the Southampton area as a mentor within the Future Worlds concept, that is probably the most important thing that I've done with them, which is to go in there and make sure they question their assumptions. Often they've made an assumption that they have sufficient battery power or that they can get to market via a given route, and yet haven't explored it. So make sure you question your assumptions. I've mentioned TRL, Technology Readiness Level. Make sure you understand where you are, because that will give you an idea of the effort that will be required to turn your concept into a product. If you're at low TRL level, risk is higher, investment is likely to be higher. If you've already got a good prototype, a good demonstrator, you're in a good position, but you need to make sure you understand exactly where you stand. I showed you a slide of a complex new product development process. Just be aware that when you're talking to bigger companies, when you're talking with companies that are expert in taking a prototype and making it a product, they may well have a process they want to follow, which you need to understand. Yeah, I think I've said that already. Decide on your route to market and your exit strategy. That's a point that I'm not sure has come out in previous talks, but do remember that you do need an exit strategy. You have to decide when enough is enough. You have to decide when you may wish to transfer your idea to a larger company that can take it forward, or you may wish to take it all the way through to product yourself. Just make sure you understand that. And please, no one knows it all. Take advice. You have a really strong network within Southampton University that can help you. Take advantage of it. You have a unique opportunity. I have not seen anything like this in other UK universities. I commend it to you. Use it. Now, in the previous talk in this series, Josh has covered the fast-moving consumer goods and markets with fewer regulatory constraints. In those markets, it's internal processes that dominate innovation. You have to be good at design, you have to be good at transferring to manufacturing, but that's about it. Chris emphasized the need to understand the customer needs and processes, especially with interfacing with big business. He is right. You need to understand your partner, you need to understand your client. In demanding markets, there are additional hurdles that you need to understand. You still require excellence in internal processes. I take understanding the customer as a given. Without that, you will never succeed. But other factors may dominate the process to product introduction. And here I'm thinking of regulatory hurdles. For example, in the medical field, you have to work with the US FDA and the UK European MDA to get their approval before you can sell a product. In aerospace, we work with the FAA and EASA. Their concern is to make sure that products are safe, and in the medical case as well, to make sure they're efficacious. In other words, they do what they claim on the box. So those extra hurdles come in some of these markets. Innovation is still possible. Indeed, it's essential, and there are good opportunities. So whilst I'm raising some cautions that you need to bear in mind, do not despair. There are plenty of opportunities for the right products in these markets. And what's even more encouraging is that I think you can work with UK companies in these fields, which makes it much easier. It's much easier to work with local companies or companies on the same island than it is with working with companies in America, in the Far East. So there are good reasons for considering these markets. In these markets, partnerships are likely to be needed to access markets effectively. So the one-man band going with a new widget that gives you a consumer experience that cannot be matched elsewhere is not likely to succeed in these markets. You often need to understand who you're going to partner with to access the market. Cost of developing products can be high, particularly qualifying them and getting them through regulatory hurdles. So it is a concern. But there are real opportunities to join up trends and to add value. As an example, in the field of military communications at the moment, it got to the stage in Afghanistan and some other parts of the world where it was despair. The military radios were not working effectively because of the nature of the terrain, but a mobile phone worked very well because you could set up local stations and talk to each other. We then took that basic technology, expanded it to form a mesh network whereby radios could talk to each other and figure out a route to communicate between the 2 points that wanted to talk to each other, even if they couldn't talk directly to each other. That made a huge difference in theatre and came up with a change, and that was based totally on the type of technology that was developed for the mobile phone industry. Sea change that came in from commercial space into the defence space, which is exactly the opposite of what was happening 20 years ago when it was defence that was leading technology. So opportunities in other areas, do consider some of these markets because there may be niche areas you can get in. Think laterally. Many examples. I'll come on to that later on when I share with you some of the examples of what I've been working on over the past few decades. In the UK, we have good tie-in with universities and R&D base. These markets, these companies, do understand the value of low TRL research. And for example, here at Southampton, there are strong links with Philips Medical, and there are strong links with many companies like that. So they do understand new ideas and innovation. There are good opportunities for complementary funding from government. It's not just EPSRC. In the defence field, for example, there's the Centre for Defence Enterprise, who will take a low TRL idea and part or wholly fund it to generate a demonstrator so that the defence chiefs can understand the technology. In aerospace, there are many examples such as NATEP, which is looking at things like 3D printing and additive manufacturing to see if it is possible to get around some of the constraints that we see in the aerospace industry. So there are plenty of opportunities for complementary funding. And I think some areas are ripe for radical change. And I'll talk about one of them in a later slide. Okay, I've got about 4 or 5 examples of some things I've done in the past. Hopefully to show you that I'm not just here spouting out without experience. Early in my career, I worked in scientific instrumentation in the field of molecular beam epitaxy. Southampton has great strength in this area in ECS, though now it's focusing more on optoelectronics, but in earlier days we were looking at some advanced 3-5 materials to give us very high electromobility. What was the spin-off of this sort of work? Frankly, your mobile phone. Because this generated a lot of the materials that were required to prove operation at those higher frequencies, and even now some of the very high-end RF devices are built with materials generated using this type of device, molecular beam epitaxy. This one won the Queen's Award for innovation in technology some 20, 25, 30 years ago. The concept basically is, you have an ultra-high vacuum, so it is very clean, and then you create beams of the particular materials you want. For example, gallium, phosphorus for gallium phosphide, and a dopant, and you then layer by layer build up the new crystal that you want. And of course you can change that composition as you grow it, which means you can have 3-dimensional structures and create some very interesting electronic properties. Done in something that looks like a very large boiling vessel. It's in fact an ultra-high vacuum equipment. The sources are at the bottom, the substrate is held upside down there, and all this is related with preparing the substrate, making sure the surface is very clean before you start manufacturing, and in monitoring the growth. Major problems in scaling this. It was easy to do with a little bit of substrate, but we had to do this with 6-inch wafers in order to make it a commercially viable process. So, So scaling was a challenge, and this is a prototype machine called the V100. Again, an interesting little anecdote. We sold a couple of these in France, and myself, I was technical director leading the team, and our sales director went to one of the customers, and I mentioned earlier you need to understand your exit strategy. Well, in that discussion, our exit strategy was we weren't going to drop the price of the equipment below 250,000. You know, come what may, we had a variety of other options, but that was our sort of walk-away position. We came away with the order valued 1 million. So, you know, it was really encouraging. Needless to say, we had a drink or two in Paris before we came back, but it can be done. We then took that concept and then said, okay, one of the problems we have is that these cells contain material that you heated to generate the beams, and you just run out of material. And at that point, you had to break vacuum, refill the source, and carry on again. And that, of course, is a very time-consuming process. To generate the vacuum of 10 to the minus 10, 11 torr that we wanted at the time required pumping for a couple of days, and you then had to bake it. You literally put, you create a furnace around this, and you baked it to drive off the gases from the metal walls. And that was another couple of days. So as you can see, it wasn't a quick and easy process. So we said, okay, how about using gases instead of molten solids? Now, the challenge was that the gases were not very friendly, things like arsine and phosphine, so we had to be particularly careful. But hey, we made it work. And this is the gas source MBE system with a gas source here, and you can see a couple of connections going through into the gas cabinet on the left-hand side. That was innovative. Again, we won some awards with this technology, which is rather nice. Real problems in measurement. How do you measure the composition? How do you automate all this? Because it has to be automated if it's going to go into production. And of course, it has to be affordable. So what differentiators did we create? What was our strategy to make sure that we could get into this demanding market? First one was closest to the customer, understanding what he wants. That's why we got £1 million for the kit instead of 250,000, because this was adapted to suit his particular needs. Innovation in the sources. I've mentioned these gas sources, and thirdly, advanced processes. So we automated all this. Essentially, you put a cassette in here, and it then just handled through. It took a couple of days to get through a cassette of 10, because this is a relatively slow process, but it made it very much more cost effective. So that was the innovation strategy in this particular market. Medical devices, medical instrumentation. I've mentioned already the regulatory affairs, and I know quite a few of you are working in bioengineering or in the medical field. The challenges we faced were appropriate technology insertion. We were looking at electromyography, essentially trying to help doctors understand how muscles and nerves were working. So you either had a needle electrode that measured the very, very low level biological electrical signals of the nerves within the muscle, or you had a surface electrode, which wasn't as good, but obviously a lot less invasive and easier to use. And you were measuring very, very low level signals. This is 500 microvolts. So it was a challenge. This is in the real world. You're talking about a real human being with skin, with lots of other things in the way of the signal you actually wanted to measure. So it was a major challenge. That's what the equipment looked like at the end of the day. It sold very well throughout the world. What innovation do we have? Technology insertion. This was the first machine that embedded a PC in it. Sounds trivial. When this was actually first generated, that was a real innovation. Was it worth doing? Absolutely. The amount of extra processing we could do, the much easier way we could store information, we could post-process information was huge. But as you can imagine, measuring this level of signal required great skills in low-level signal processing and in new algorithms. What differentiators do we have? I mentioned the PC. We also had better technology. This was one of the early days of the digital signal process, and we embedded that to try and extract information from these signals. We were the first networked machine, and again, that gave us an edge with the customer. But perhaps the one that I'd like to draw your attention to is our understanding of the medical regulatory process. And that was a key differentiator. The standard process is You build your equipment, you take all the measurements, you prepare a file, and you submit it to the FDA or the MGA for them to assess. Hang on a minute. The first thing that happens is they sit on it for 6 months, and then they come back with a series of questions. So what we actually did was we submitted an incomplete medical file quite early in the device life cycle, and we knew that by the time they'd look at it and come back with the questions, we could answer all the other bits. That typically saved us about 4 months in terms of time to market. Trivial innovation, but it made a big difference. So our strategy there was to be very good at regulatory processes, to get it in quick, to make sure that we were ready to answer the questions as effectively as possible. Turning to something a little bit different, in the defense field, when I was with Cobham, one of the things that we did was we delivered the vehicle intercom systems for all the US Army's armoured fighting vehicles, everything from the Abrams tank through to Humvees that were used by special forces. And it's intriguing to consider that the US Army was using a British intercom system and the British Army was using a Canadian one. I have yet to understand that one. As is always the case, there were good reasons for it at the time, a lot being down to the contracts and who owned the contracts. So when we came to look at the next generation of these, and this is some years ago now, but perhaps a little too recent for me to be able to give you too much detail, the key thing was something you are also good at, digitization. The old systems, whilst they were digital, were designed for voice. The new systems had to be designed for voice and data. We're talking about the Internet of Things down to vehicles. It is true that, video information from a vehicle could be relayed all the way back to Washington if need be. Why you'd want to do that is a different question, but you had the ability to do it. So we designed a new system, and the key differentiator was exploitation of what we had there already. We designed a system that could reuse the existing wiring, which meant that in vehicles like Bradley that had been in service for 15 years or so, you could just take out the old boxes and put in a drop-in replacement box that gave you this new capabilities. You can imagine the amount of money that saved the customer. He didn't have to rewire all the vehicles, which is extremely expensive, particularly if some of the wiring has to go through the armour. And it was a winner. It's what gave Cobham the contract for the next generation vehicle. How did we do it? And this is the point I made earlier on about thinking laterally. So we recognized that we had wires with certain characteristics. We recognized we had to get through difficult things like turret slip rings, which are quite challenging in terms of the frequencies they let through. So we did two things. We took the coded orthogonal frequency division multiplexing technology that is used in your mobile phone, and we adapted it to suit this particular environment and came up with a little box that was the Internet Interface Unit. And that coded the information. We were getting, I know it doesn't sound high, but compared to what it had before, we were getting 10 megabits per second, maybe 20 on a good day. But it was adaptive, it was self-corrective, it used, my answer to all questions. It used Ethernet and it used IP. And when it comes to digital, if you use Ethernet and use Internet Protocol, you have a huge range of capabilities. And that was a major change to the way this worked. We developed wireless units using the same technology, and it's a robust product that is very soldier-proof. Again, just to give you an example of the importance of this. In theatre, we had vehicles with our old intercom system, and the Marines, the US Marines, because the US Marines always do something different to what the US Army does, had a different intercom system. And both were used in theatre. And what they were experiencing is that it was a rough environment. They had improvised explosive devices going off, explosions near them. They were firing their cannons in unexpected ways to get out of trouble. And occasionally, the systems would see a glitch. Now, the big differentiator in our system is that a glitch would reset itself within 20 seconds, whereas the competing system, which was based on more traditional PC technology, was taking 3 to 5 minutes to really come up fully. Why does that matter? It matters because the intercom system is the link between the commander and the driver. So if the driver wants to say reverse and let's get out of here, he wants to do that immediately. And if your intercom system's down, he can't. The end result, the US Marine Corps swapped to our system. So, it's the unexpected that sometimes works in your favor. Scientific instrumentation. I was very fortunate in working in an SME, which was only, there were about 5 of us, and what we had was a mid-infrared spectrometer. Now this was based on some key differentiators, but the innovation was a novel detector. The detector is not very clearly seen here, but essentially this is a back-edged silicon wafer with a pyrothermal detector, which was patterned on the top there, a pyroelectric detector, that's what I meant to say. And by using a mirror, because these mid-infrared frequencies, glass and most materials are opaque, so we used a mirror as a spectrometer and then focused the different wavelengths onto these individual detector dots. They actually were lines, and we could then measure the electrical signal that was generated by the impinging infrared light. Really good, really fast. Novel detector, the configuration was novel. This was about the size of a shoebox, and the probe, allowed essentially the head to get into the chemical soup whose composition you were trying to measure. What were the applications? The applications mainly were real-time monitoring of chemical reactions. What area did we really want to get into? Pharmaceuticals, because there's a lot of money in pharmaceuticals. Could we get into pharmaceuticals? Not a chance. And why was that? Because we'd have to qualify all these materials as safe for use in pharmaceutical applications. So what did we do? We targeted agrochemicals first, because agrochemicals have a much simpler regulatory environment. But the end target was the pharmaceuticals. Worked well. We were partly funded by a large pharmaceutical company who at the end of the day, when we went to the next stage of funding, says, okay, exit strategy, out you go, we want to take this back into the company because we think that this will give us a commercial edge. And we did a deal. That's the way it goes. Now let's think about the future. Now you may think that defense, aerospace, all these markets are actually quite conventional. Are they? Some of the work I've been doing at the UK aerospace industry has been looking at the next generation aircraft. Now let's be honest, we're not talking 2020, we're not talking 2025, we're talking about probably 2030. But a lot of things are going to change around us. A lot of change that you are going to be driving. Are we going to see liquid hydrogen as a fuel for cars? If so, it'd be really, really attractive for aircraft because it's a very efficient fuel. It's a very weight efficient fuel. It has about 3 times the energy density by weight of kerosene. But it is only about 1/5 the volume efficiency. So we need more volume, but it's less weight to carry around. It also enables cryogenic use because it is cold. We can use it to cool superconducting motors. And we come up with the all-electric aircraft. These are not gas turbines. These are electric motors. The primary energy source will either be a battery, a fuel cell, or for longer-range aircraft, those working in combination with a simple, optimized gas turbine whose only job is to generate electricity. And that electricity is then stored and used for propulsion or whatever. Now, if we go to a blended wing body, and here we see a NASA concept. This was the NASA X-48B, which was actually built at Cranfield University in the UK. And if you look at this, you can see that the middle of it is good space for passengers, but there's a transition period which is it's not big enough, you can't stand in it, but it gives you volume in which you can put your liquid hydrogen tanks. And that's a very efficient aerodynamic design. So you've got some differentiators, but this at the moment is concept. I'm not going to see this delivered, but you might, and you could be part of the team that innovates in these areas to create these differentiators to deliver the next generation of air transport. So I've had my 40 minutes. I'm just going to summarize a few key points, and then we'll take some questions. I hope I've shared with you some thoughts on innovation. I perhaps haven't been as clear as I hoped in terms of the strategies, but I hope you understand the constraints that allow you to develop your strategies. I hope I've built on earlier presentations in this series of talks. And as I've mentioned, there is plenty of scope in many areas to take advantage of new technologies. I think I have considered some of the aspects that need to be tackled when you're addressing these more difficult markets. And the key points I think that I extract from the consideration is, please think through the complete new product development process. Don't just focus on the idea. Think through the route to market, the commercialization, any regulatory hurdles, and of course, the customer is paramount. Partner where appropriate. You may need to partner for routes to market. You may need to partner to access technologies. Don't be scared of it, but do it sensibly. I've just shared some personal experiences in innovation and just given you an idea of some of the things that can happen throughout a career. And I hope I've encouraged you to consider these sectors for your future careers. Innovation is at the heart of what the UK has been good at, and what Southampton in particular provides a very fertile environment for you to take your ideas forward. Just consider it. The point I'm sharing with you is, please, you don't all have to be individual entrepreneurs. You can work as small teams. You can actually take that spirit into large companies and help them in the future. There are many opportunities. You've got excellent support from Future Worlds, from the research and innovation services within the university, and from mentors such as myself. It's almost a unique opportunity. I'd be disappointed if you didn't take advantage of it. And finally, have fun. The future is yours. It's a difficult question to answer simply. I think at university, the key thing you need to do is to understand the process. You need to understand the key elements. There will be design reviews. You need to understand the concepts of that. There will be interfaces between different parts of the company. You know, engineering does not work in isolation. It works hand in glove with finance, and of course marketing and sales provide the environment within which products are developed. So you need to understand those. There are plenty of good references. I don't know enough about current teaching in the university, but I'd be surprised if some of these issues are not considered. If you have an idea, you have a means of getting advice. If you want more detail on that, speak to Ruben. Let's see, what mentor is best suited to advise you on how to take your idea forward. Perhaps what I didn't emphasize is that there was method in my madness. There was a common thread going through it. My real interests are embedded control, instrumentation, and electronics. Now, I'm of the generation, the dinosaur generation, where, I owned the 308th PDP-11 ever built. So, I really was a child of the computer age as it emerged. So you have to bear that in mind in some of my career transitions. I started in the defense field in semiconductors because I really wanted to make the world's smallest, fastest transistor. That's what drove that. And we had a good go at doing it. I then took an idea out into industry, which was essentially looking at the problems of patterning, of very small patterns for semiconductor devices. I took it down a route. It worked, but we ended up on a limb. So at that point, I had to reconsider what I wanted to do. I was then given the opportunity to look back at my core and move into the medical field, medical instrumentation. The core theme being electronics, very high-level signals, control, measurement. So I did that. And I then had the misfortune to be promoted, so I think I stopped being an engineer and became more of an engineering manager, which in many ways I still regret. You actually are what's fun. Thinking of ideas, making them happen, engineering. That's what is really enjoyable. Engineering management is a necessary evil. Now, I enjoyed it because I could steer programs. but I missed the hands-on. To some extent, I still do. So in medical, I was with Vickers Medical, then got, originally with a company that made that equipment, I measured the electromyography equipment, then got kicked up to medical division, and then went up to head office, looking across the Vickers group as essentially CTO of the Vickers organization. Now, you may recall, but one of the things I've done in my career is I've been in the Army Reserves. So I've always had an interest in military things. And the nice thing about Vickers, what is it had a medical division, a defense division, and a special materials division. So it gave me breadth. So that was a good step. I enjoyed that. And then after that, when Rolls-Royce took over, they wanted me to move to Derby with, I need to be careful what I say, but with respect, wasn't quite what I wanted to do. No, I had children about to do O-levels and A-levels, so it wasn't, I couldn't move. So I said, thank you very much. And then I joined that small company in mid-infrared spectroscopy because it was a fascinating challenge. You know, that was getting back to actually making something work, which is really, really great fun. As I said, did that for about 3 years. The company got reabsorbed into a large pharmaceutical. I took 6 months off because I was shattered. And perhaps what I should have mentioned is running or being in a small company is very hard work. Okay, so bear that in mind. You know, you give it everything you've got. You always should, but it's always just that little bit more if you're at the heart of it. So did that, and then after that, took a bit of time off and then went back into kinetic because of my interest in defense. And that was your comment about the weapons division. There we were looking at advanced missiles, we were looking at assessing technology that was being developed in other countries, we were looking at some of the challenges associated with advanced explosives, with propellant materials, really good work. Kinetics, a very, very capable scientific organization. After a few years there, I didn't see eye to eye with senior management. It happens, so I left and I joined Cobham. And I was with Cobham for the past 9 years before I started my own consultancy. Cobham is an interesting company. It has its challenges at the moment, but it will get through them. So, as I say, there is a theme going through. It wasn't quite a random jump in science. No, because when I say incomplete, it meant that, you know, we hadn't got the results from the final equipment. We had results from prototype. So I had perfectly sensible results to submit. So I wasn't submitting blank pages. I was just submitting pages that said to be confirmed and things like this. So when it finally got through the process and got assessed, the plus side is it gave them easy questions to ask.
You got the answers.
And we had the answers by then. Yes, firstly, look for a grandfather. Look for existing technology that is similar to what you have so that you can make the FDA's job easier. You see, that particular item I showed you of medical equipment was based on an earlier one. So we could say, these tests operate the same way as those. We've done it differently, here's how we've done it differently, but the results are essentially the same. And here are some new tests that you then need to consider in more detail. Here's the evidence. So the grandfather clause is important. It's important in aerospace as well. Because when I look at some of the aircraft that are currently flying, some of them rely on technologies that were tested 20 years ago. And in all honesty, even though they're perfectly safe, they haven't got the body of evidence other than use. You know, because those standards were different at the time. So look at grandfathering if you can. And secondly, identify where the areas of risk are. Do a thorough risk analysis and make sure you have good answers to those before you go into the FDA. Yes, I deliberately tried to stay away from that area because it's been covered in previous talks. There are areas, I mean the UAV field, whilst it's a minefield because there are so many companies there, is an area where small companies can make an impact. There are areas in information technology where small companies can make an impact. I was having a chat with a couple of gentlemen before over lunch. One of the key challenges is cybersecurity. So if a company has good technology in cybersecurity, it could certainly apply it into these areas. And that, I mean, another example from the defense field. There's a particular company in the UK in communications that has evolved some very, very good processes to frankly, they're in the gambling and banking industries, and they're looking at data, and they can channel the relevant bits to the appropriate people. What's the importance? It maximizes use of your communication channel, because everything is not going everywhere. You know, it's being selective. And that core technology is very, very useful to the defense field, because you have the same problem. You know, it's the same concept. You want, you know, everybody says, okay, we've discovered the enemy is there. Who needs to know? Everybody doesn't, because all it'll do is confuse them. You just want to tell the local units what's been found. So you want to route the data, and communication bandwidth is always a challenge for the military. You know, there's never enough of it. So technology from banking and gaming is actually very useful in defense, and that's a small company. Okay, so yes is the answer, but in niche areas. Taking the first one first, how you price it. Firstly, you need to understand what your competition is. If it is unique, then you can price it higher. You also want to look at it from a customer point of view. What revenue stream is he going to get from it in that particular case? And that gives you another metric you can use to sort of position it. Thirdly, you need to look at availability of money. So in that case, we made sure that we had in our pocket a leasing agreement pre-set up that could go anywhere from $1.5 million to I think the break-off, it was less than 400,000. They weren't interested. They couldn't make enough money from the lease. So it allowed the customer to fund his project. So you do a fair amount of background work. To be honest, you price it as high as you can. And we went in at $1 million, expecting to be battered down. And because the case was compelling, and because frankly the customer had little real alternative, and it wasn't his dominant cost. His dominant cost was going to be the running costs, the raw materials, you know, so he could see the business case. So at the end of the day, I suspect what he said was, I want to keep these guys on side to make sure I get the best possible service. If something goes wrong, it's worth $1 million to me. How did we do the discussion? Can't remember. Right, we started life looking at pharmaceutical chemical production because there's a lot of money there, and they were having problems with batches, essentially not performing the chemistry they expected, because the system at the time was you took a sample, took it to the lab, put it in the MIR spectrometer, and got an answer 3-4 hours later. Too late. You know, the brew has changed. So the whole concept was to give them immediate feedback so they could adjust temperatures, pressures, compositions to make sure they got the maximum yield. So that was the differentiator in the concept. As I said, the headache is that pharmaceutical equipment, pharmaceutical chemicals are life-threatening, so hence materials you handle have to be appropriate. Now, mid-infrared, in fact, we actually worked with Southampton University. Mid-infrared can only be transmitted by certain glasses, and those glasses are chalcogenides and contain arsenic. Do you want arsenic in your aspirin pill? Not really. So there was a compatibility issue. In pharmaceuticals, it really didn't matter because a trace of arsenic was irrelevant to them. Sorry, in agrochemicals. So we've targeted that market first, even though there were fewer potential applications because the chemistry was similar. Now, we developed chemometrics. So you see, our first mistake was we generated an equipment that was a spectrometer. There you are, there's the spectrum. And our main funding company had the chemists and the analysts who could interpret it. When we went to other companies, they said, what does this tell me? So we actually had to develop the software working, in that case with Bristol University, to actually analyze the spectrum, look for the chemical bonds, and then come up with the chemical composition that that spectrum actually represented. And that's when we ran out of money, and our main funder said, no, thank you very much. I've got what I want. I'll take it back in. C'est la vie.
Well, thanks very much, Vincent. Let's give Vincent another round of applause.